I'm a professor at Princeton. And what I'm going to talk about today is two different things, right? So one is on the frequencies of what we call the terahertz. How do we think about terahertz chip scale systems for communication and sensing? And I'll briefly touch about sort of emerging ways where AI can help in designing such systems. So again, as I said, I have two broad areas of research, one of which I'll not cover today. So one area of research is millimeter wave and terahertz systems on chip, which you will see mostly in the presentation. But we also do work in the biomedical space for miniaturizing sensors, ingestible sensors, sensors that can go into your body and give you information within the body, optics, and so on and so forth. But that's not the topic of today's talk. We have a vibrant lab. You can see sort of group pictures. The lab members come from across the world. I know we have people from India, Turkey, Iran, Egypt, China, South Africa, everywhere. And so you can see my students here, my postdocs, and I'm sort of here. And we have fun. So if you are around New Jersey, let me know, and I'll be happy to show you the campus. So let's just get started. So first of all, there's a lot of applications and a lot of emerging areas in what we call the millimeter wave and the higher sub-terahertz and terahertz frequencies. So starting from 30 gigahertz and below, going up to 100 gigahertz and above. And the applications are basically two-front. One is communication, wireless communication. At high frequencies, essentially means higher data rates, higher capacity, and so on and so forth. Why do we need that? So in many of the cases, you need for backhaul applications. So instead of laying an optical fiber, you might have a very high-speed backhaul link, which is wireless. New emerging areas in space, in satellite communication, often go up into millimeter wave frequency ranges. Also for high data rate throughputs for many emerging applications such as AR/VR. On the sensing side, automotive radars using millimeter wave frequencies are everywhere. You can buy a radar for your car for $100 or say 7,000 and 8,000 rupees. But now people are moving to higher frequencies at 140 gigahertz for high resolution and sensing. And you have to think about that when you're developing radars for these kind of for automotive applications, the cost is the key. You cannot sell radars at 50,000 rupees or 60,000 rupees. You have to sell radars at 5,000 or 6,000 or 7,000 rupees, right? Because to be able to put in multiple radars within a single car for 360-degree coverage, cost is the key. So that's something you have to think about. You can use radars for other applications, not just for automotive. You can use radars for gesture recognition. This is a project from Google solely that interacts with a watch at a 60 gigahertz radar, right? So when you think about radars, you think big giant systems. No, not anymore. These radars get into your smart watches. You can think about applications such as security. This is an image of someone carrying a gun, imaged at 675 gigahertz at JPL NASA at quite a distance. I forget the distance, around 20 meters distance. And so these waves can penetrate within clothing and give you information that you could be hiding something. So there's also security applications as well. Coming back to the communication applications, you can think about really high-speed directional data links, right? So at these frequencies, these are not omnidirectional Wi-Fi or mobile kind of wireless. These are very directional, almost like laser beams. That can go from drones to drones or drones to a ship. You can think about these high data rates for applications in data centers that can avoid this kind of wiring that you see here. You can have applications such as data rates and stuff like that. But the point is that all of these high frequency interfaces, whether it's for communication or whether it's for sensing, primarily or almost exclusively relies on this idea about multi-antenna systems. And that's very different from kind of Wi-Fi and mobile-like applications that you use now. In your current And what has happened in the last 20 years is that in the same way, Moore's law has enabled us to scale really basic integrated circuits, 50 years ago into this, AI processors that has, more 21 billion transistors in them, right? So if you just think about the Tesla V100 graphics IC, NVIDIA, it has 21 billion transistors in them. That's 3 times Earth's population. Earth's population is like 7 or 8, right? It's 3 times more transistors on chip than there are people on Earth. Just imagine the scale of integration of that. And the same, scaling that we have used for digital processors is now being used for RF and high frequencies. And that's the whole idea. So just to give you a sense of what is the scale here, right? This is the first planar IC in 1960 that had 3 to 4 transistors. It was basically a flip-flop, one flip-flop, the whole wafer. And now we have these kind of very complex systems. But the additional thing about it is not just how much transistors you can pack on a chip, is what's the cost of a single transistor per chip, which is almost zero. So in 1961, Texas Instruments won the purchase order for the first Apollo project, the one that went to the moon, carried people to the moon, in 1961, and they were charging $1,000 per gate. So that's an AND gate, NOR gate, those kind of basic gates. Today's chips have billions of gates, right? So it's $1,000 per gate. But now you get 100 million transistors per millimeter square of silicon for $1. Okay, so from $1,000 per gate to $1 for 100 million of these. Okay, so think about the scale in which things have changed in the last 50, 60 years. That's just one human generation, right? In one human generation, things have completely changed. And so the same thing has happened in the millimeter wave and terahertz system. So this is, for example, a Qualcomm phased array that it operates at 28 gigahertz that go on your several smartphones. My phone has one. So if you can see this phone, it has 3 phased arrays on the sides operating at 28 gigahertz. And you can see those 3-element phased arrays on this side, on that side, on the other side. And you can see the size of these arrays, right? Very, very tiny. Fully packaged with antennas and RF chips and so on and so forth. But this didn't happen all of a sudden. People have been working on this for the last 20 years, I would say. The first phased arrays came from Caltech in the millimeter wave band almost 20 years ago at 24 gigahertz and 77 gigahertz. And Berkeley was doing a lot of work on 60 gigahertz phased arrays. My PhD thesis on the right-hand side showed the first terahertz phased array in the world in 2012. This was 300 gigahertz phased array in a single chip system. Okay? So that is really exciting. So now you can build very, very high frequency, very, very complex systems in silicon chips at very low cost. So these would be, $1 in volume production, and that's the whole point. Another really great applications is space, right? India is doing fascinating work in the space. We're all really proud of it. Chandrayaan, for example, was a success story of really unimaginable options. But space communication, satellite communication, that's another emerging frontier that we should also be thinking about. Amazon in Project Kuiper is deploying thousands of satellites in space. SpaceX is also deploying satellites in space. There are many Indian startups trying to do that same thing. And a lot of these sort of LEO communication would happen with phased arrays. So this is an example of a SpaceX phased array. You can see the size of this, right? It's pretty large. And if you zoom in there, you can see these circular spots, right? All of these are antennas, okay? So you can count the number of circular spots. You can get a sense of what the size of these phased arrays. And these are typically 1,000, 2,000 element phased arrays, pretty complex design. And if you take it off, you can see these sort of, circularly polarized antennas, that all of these antennas are connected to silicon chips. There are hundreds of silicon chips embedded into this phased array system. And the reason this is not millions of dollars, but maybe hundreds to $1,000 is because the silicon chip cost has gone to that point where you can make the system work. Okay, so that's a fundamental point. And so what we want to do for our work is that these complex terahertz instrumentations that take large, bulky, expensive to manufacture could be reduced down to chip scale systems, and that can start emerging sort of commercial applications that are really interesting for intelligent sensing and communication. So this is just an overview of what the space of terahertz is. I just want to give you a little bit of history of how the chip technology in terahertz evolved in the last 10 years. And why we are in a new design paradigm. I'll give you some examples of terahertz chips. I will not go in deep about each of these. And then I'll sort of end by talking a little bit about how AI can help in designing some of the systems as well. Okay? So there you go. So if you have heard of the terahertz technology, you might also have heard about terahertz gap. But let me just define terahertz for now, right? Anything above 100 gigahertz is generally called terahertz. Some people call it above 300, but let's, for this discussion, just limit to anything above 100 gigahertz. In 2007, which is like 16 years ago, this is a very famous paper from Nature Photonics, where basically said, well, there's a terahertz gap. There's a lot of stuff happening in microwave. There's a lot of stuff happening in optics, but there's nothing in the midway, which is the terahertz gap. In 2008, the first silicon terahertz systems emerged. The first one from UCLA and UT, University of Florida, 2008. Okay, this is the red dot here. This is power. This is frequency. So the power of these silicon, chips were tens of nanowatts of power. So really nothing. In 2008, which is even 5 years ago, we wrote a paper in Nature Electronics with some of our collaborators, and we said, well, look at where from 2008 to 2018, in 10 years, silicon has jumped from tens of nanowatts of power to milliwatt level of power. Tens of nanowatts to milliwatt level is almost 100,000 to 1 million times more power. Okay, so that's amazing. And the reason that happened is not because your transistor technology improved by 1 million times. It's because people understood that you need to think about power combination, new ways to think about designing the system, and move away from the classical RF design process. But in the long story short, you can now generate milliwatt level of power in terahertz and silicon. In our own work in the last decade, from say 2011 to 2021, 2022, you can see this is just our lab, and if you take the terahertz chip scale system from any committee, you will see the systems have become much more complex as they go forward. So we started with phased arrays back in the day, but now we've gone into silicon terahertz cameras, silicon terahertz spectroscopes, arbitrary waveform generator, metasurfaces, even large-scalar phased arrays, high-power phased arrays, physically secure links, and all of these sort of more complex systems have emerged in the last 10 years. The challenge is the following, okay? If you're trying to do something at silicon, there's something called the Fmax of a silicon device. And that is basically tells you what is the frequency limit of amplification. So as an example, if you look at the plot on the right-hand side, the blue squares are where silicon CMOS are, which essentially means their Fmax is 300, 400 gigahertz. Essentially tells you that you cannot amplify signals above 300 gigahertz in silicon. Okay, but if you look at indium phosphide, for example, their Fmax have crossed 1 terahertz. Okay, so indium phosphide 3.5 devices are much better when it comes to silicon. So the question is, how should we think about designing? So why don't we just use indium phosphide as an example? Well, the reason we cannot use indium phosphide for all commercial applications is because their cost and reliability. As I said, the cost is the king for these complex systems and commercial scale. So silicon is the only option at this point. Indium phosphide, you can use certain some of aspects in defense applications, but it becomes very difficult to do in applications. The gallium arsenide power amplifiers are still used for mobile because power amplifiers efficiency is the key. Okay, so when you're thinking about silicon as a device, it's much weaker compared to 3.5s. Okay, so I use this picture to demonstrate the design process, and you might have seen this before, but this is really telling. This is really the picture that tells you how weak silicon is compared to a 3.5. Okay, so you are basically fighting a battle that you cannot win with silicon. Okay, but the power of silicon is not the power of a single device. The power of silicon is the power of a billion devices. It's almost like power of India, right? You have billion people. And so if you harness the capability of the population or multiple transistors, then you have a battle that you can win, right? And so the design process of silicon terahertz systems is basically this picture, which is you don't try to optimize every device, you try to collectively harness the power of many. Okay, and so in our whole work, you would see not one single large device that's working. You would see a distributed system where many of these devices are working coherently with each other, enabling these kind of high power systems. So that's the new paradigm. If you have seen these kind of classical architectures where you have, oscillators, power amplifiers, mixers, antennas, these systems are harder to scale at terahertz because your device is not working efficiently. So we really need to think about it fundamentally. And as an example, what is the fundamental idea here? If you think about any transmitter, okay, what is a transmitter? If a wireless transmitter basically transcribes information, so digital bits, to some radiated electromagnetic fields through the antenna. Okay, so all you care about is how information gets transcribed into electromagnetic fields or modulated in electromagnetic fields. How do you go from information to modulated fields? This is one approach, but this is not the only approach. Okay, and so the question is, if you think fundamentally that at the end of the day, all you care about is some modulated electromagnetic fields for a transmitter, information to field, and for a receiver, it's field to information. And the way you connect these two dots could be many different ways. I mean, this is one way of doing it, but this is not the only way of doing it. And so we have explored this space where these transmitter systems looks very different from classical sense. So I'll just give you one example of it. I showed you the first terahertz phased array that we built 10 years ago. And if you look at closely to this terahertz phased array, they don't patch antennas or dial antennas or any of these antennas that you know of. So we did this following calculation. We basically said, well, if I want to create a single chip, what is the oscillating current that will be optimal to radiate out of silicon? Now, silicon is a substrate, a high dielectric substrate, so you have to think about surface waves and all kinds of modes. Long story short, we figured out that instead of patch antennas or dipoles or any of the antennas that you know from textbook, you have to create a completely different kind of a current field. And you can see that there are 6 different loops here, but it's basically an infinite array. And all of these loops behave like traveling wave loops. So it's almost like a traveling wave in each of these loops, okay? But no antenna that you typically know creates circularly traveling wave antennas. So what we did was we have transistors and we have antennas on chip, right? And so we basically created a new structure, what we call distributed active radiator, where these loops are connected with transistors in a weird fashion. So what happens? You see, if you've taken circuits class, this looks like a classical oscillator, okay? So what happens is that, by the way, at 300 gigahertz, all of these things are on chip. This is not packaged antennas. All of these are realized directly on the chip itself. So when the chip comes out, the antenna's there, the circuit's there, everything is there. So the way to operate is that if you create this structure and you put a voltage bias, then it creates an instability. These two loops then behave like a transmission line. Okay, so if you've read transmission lines, you would say transmission line, transmission line, transmission line. But the same loops, okay, now start behaving like a radiator at the second harmonic. Why? Because if you think about the fundamental frequency of oscillation, these loops behave like a differential transmission line. So it's 0 and 180 and so on and so forth, and 135 and 315. They're all 180 degree apart. But if you took the second harmonic injected by the current, 0 times 2 is 0, 180 times 2 is also 0. So you get 0 and 0. 315 times 2 and 135 times 2 are both 270 degrees. So you see that now these two currents start moving in phase. So you have a fundamental oscillation of 150, but the second harmonic 300 gigahertz start moving in phase. And so the same loop that behaves like a transmission line now starts behaving like an antenna. So it's no longer a microstrip line that is a microstrip line at all frequencies. This is sort of a new kind of a system where you are engineering the surface current based on the boundary conditions with the circuits itself. And that changes with frequencies. So you basically, with this, essentially what happens if you put a 1 volt with a battery on the system, a 300 gigahertz waves radiates directly from the chip. Okay, and that's the whole point. So what we did was we created a phased array out of this, and so this is, you can see this is a single chip phased array. You can see those sort of circular loops here with transistors in there, but then you have all the distribution systems to control amplitude and phase. And you can see the power coming out of the system at 280 gigahertz, and then you have complete full electronic control of the beam itself. Okay, so this is on the transmitter side. On the receiver side, we were trying to build a spectroscope. Now, how do you build a spectroscope? If you use a spectrum analyzer, you can see that it's a very bulky instrument, right? And so what we created is a terahertz spectroscope. And what we did here is the idea that, again, think about it. At this high frequency, your antenna is on the chip. And the question is, we don't have to think about the antenna as a 50 ohm antenna that's connected to a receiver. Your antenna has a lot of interesting information that we typically neglect. So what we basically said is the following, which is the antenna itself is a spectrum analyzer. Why? Because if different spectrum of the waves, when it strikes an antenna, creates a different current distribution on the antenna. So if you had a 100 gigahertz wave, it has a certain current distribution. If it's a 150 gigahertz wave, it has a different current distribution. And so if you could sense those current distribution on the antenna itself, then you can do signal processing and then figure out, well, you can get information just from the antenna on the spectrum of the incident signal. So that's your spectrum analyzer. So that's what we did. We have a classical log periodic antenna, but unlike an antenna, there is no signal coming from the center. What did we do? You see those black dots on the antenna? There are 84 receivers connected to a single antenna. 84 detectors directly connected to a single antenna, but no signal coming from the middle. And what are they doing, these detectors? They're measuring the local field. So you basically have mapped local field distribution spatially. That is unique to the spectrum. So every spectrum that it finds, you will get a different distribution of these color maps from the antenna. And then you can take it out and sort of process it. This experiment from 40 gigahertz to 990 gigahertz. 990 gigahertz, so it's almost like 1 terahertz, right? So from millimeter wave all the way up to terahertz, and you can see that we excite at different kinds of frequencies, 66, 980 gigahertz, and just from a single chip 84 detector DC responses, we can estimate very accurately what frequency the incident wave is. So what frequency of the incident is, it still excitation, wideband excitation, we can do all the time. Okay, so again, what I'm saying is that you really need to think about these things very differently from classical RF systems where things are very partitioned, right? So one person designed an antenna, another person designed an NNA, another person designed a mixer, another person designed the baseband amplifier. They all connected together with 50 ohms. This is essentially from electromagnetic fields to information, and everything happens together collectively. And so it's like a new kind of system that we are talking about here. So let me give you some sort of more recent works of these kind of terahertz systems. So first one this appeared on the cover of Nature Electronics a couple of years ago. And this is the idea of terahertz programmable metasurface. So what is metasurface? So here's the idea. Okay, we talked about millimeter wave terahertz being high directional communication. And one of the problems with high directional communication is what is described on the left-hand side. So you imagine that you have multiple users, you have an access point, you try to create a beam, but if you have a blocker, say some person walks in the beam, you don't lose your cell phone connection, right? You go out of your room, you don't lose your cell phone connection. But in millimeter wave terahertz, because a beam is like a laser, like a directional beam, if someone walks in front of you, in front of the beam, you lose connection. And so the whole idea about this is that, well, if there is a blocker, this could be an object or another person, then can this access point direct to this surface? It's basically a reflector array, okay? And by a programmable reflector, it's almost like a mirror, programmable mirror, right? So that can direct the beam again and connecting the link together, right? So it's almost like a surface where you have an incident beam and then it can sort of manufacture a reflected beam. There's a flat surface. Then imagine that there's a car coming in, and this beam cannot reach the car, so this beam can reach the surface, and the surface can reach the car. Okay, so you can deploy this either in home or outside. The idea about these flat surfaces manipulating the beam is also getting traction in optical cameras. Optical cameras now use lenses. So, but there's a new research of research that's happening where lenses are not bulky; it's flat. Okay, it's almost the equivalent of RF transmit array in the optical domain. So lots of interesting things are happening on that front as well. So again, I don't want to go to the details of calculations, but build a terahertz metasurface, something that operates at terahertz, is very, very difficult. All our past work was based on very complicated electromagnetic tools and thermal control and stuff like that. So there was no prior work on chip scale metasurfaces before our work, which came as a cover of Nature Electronics. And you can see what it looks like first. So you can see there are 4 chips that we tile together, and they're bonded, right? It's almost like a Lego piece. Okay, in Lego you build one with multiple and you create large systems. Here also it's like a one single chip. You put another one. It's all, you can tile them to create large surfaces. If you zoom into this, how does it look like? It's like this looks like flower petals. Right? It's almost like a flower petal. I'll tell you why it looks like a flower petal, but these are like large-scale arrays of flower petals. But each of these is basically a meta element. And you can program this. You can program the scattering of this behavior with respect to an incident beam. Okay? So how does it work? It works in the following way. Okay, so you take this surface, you send in a wave, say terahertz. On the other side of the surface, it can do anything. So it can create beamform, so you can scan the beam in space. So you can take your horn antenna, shine this surface, and this surface can beamform. So you've basically turned your horn antenna into a phased array at terahertz, okay? Very powerful. But how does it do that? Well, the fundamental idea here is the following. You take a resonant meta element, like the C-shaped, and by controlling the aperture, like how open the aperture is, or the orientation, you can control the amplitude and the phase of the transmitted wave. Okay, so then what you can do is you can have many of them, and each of these elements can have its own amplitude and phase, and so you can always think about this as a building phase. But once you have fabricated this, is right, the amplitude and phase cannot change, but this thing cannot change. What we basically thought is like we create switches in these structures, and then by opening and shorting several switches, you can dynamically create different kinds of rotation. So if all of these switches are on, you can see you create a C, but now if you rotated the 1 and the 0, the opening sort of comes here, right? So by playing with the digital states of this, you can manufacture, or you can basically program on the fly the scattering behavior, right? And so that's the idea. So we build a chip, and you can zoom into the chip, you can see this meta element here. There are transistors connected to each of them that can open and short. And by closing and opening different shorts, you have different amplitude and phase coming out the way. Okay? So how does it work? I mean, what is the measured result? So imagine the surface. What we can do is the following. We can make it's just programmable. It's digital. It's connected to a laptop, right? This surface can make it transparent. So the phase again be able to form. So this is some measurement results that you can see. So you take one chip, you see this part of it is opaque, this part is transparent, this part is opaque. By opaque, I just mean that this is digital control of the scattering states. We didn't put any film on top of it, right? So, and then you can see that you can create and we use simulated results, measured results. It's almost like a spatial light modulator that you can create essentially any kind of electromagnetic field patterns. This measured results of beamforming at 300 gigahertz. So we basically took the surface, put a horn antenna, and by creating different phase gradients, again, digitally, you can basically scan the beam in space, okay? So now you've created a low-cost phased array, okay? As I said, cost is the king. This chip, when you manufacture at scale, would be a few dollars, okay? You put on a horn antenna, you've converted a $100 horn antenna into full-scale terahertz, okay? So that's the kind of innovation we're talking about here. And then what we did even some pretty, hologram, right? So optical holograms. We created a terahertz hologram. And what we did is we had the horn antenna shine it, but then we created the amplitude and the phase on this surface in a way that it projects Princeton University or PNU at terahertz. Okay. So this is not something you can see, but this is something you can measure. And you can see the measured results of the P and the U. This is this is a very difficult measurement, but you can see it almost looks like a P and U, right? So you can basically create any kind of field projections on the surface itself. And this was the first programmable terahertz projected, but we have done these things with millimeter wave frequencies as well. So this is an example where we build these chips at 60 gigahertz, connect with programmable reflector arrays, and it works in the following way. So imagine you have a transmitter, okay, and the receiver is somewhere here. What we do is that the transmitter shines the beam here. These chips absorbs the signal, amplifies it, and directs it towards the receiver. Okay, so if this chip is on, you see the QPSK link being formed. If I turn off the chip, then the signal basically goes, hits it, and the angle of reflection is the angle of incidence, so it basically reflects in somewhere direction. And you can see here, it violates Snell's law, right? So this reflector array absorbs the signal and can direct it towards this green beam. So your angle of incidence is not the angle of reflection, because you can do this with chips. You can absorb the signals and amplify it and send it, and thereby creating this kind of links that you wouldn't have otherwise, okay? So now you can have these chips connected with the antennas and build very, very large scale array. Let me give you more example of how you turn this into something more interesting. So one of the things that we have been thinking about is security. Security for wireless communication, okay? And we typically do security with encryption, so you encrypt your data. The challenge with just pure encryption at high frequency is that encryption takes time. And in many of the applications, the latency is the key. So what we basically started thinking about is there a way we can enable encryption in the electromagnetic waves itself, okay? So this is what we wanted to do. Imagine you have an orchestra, okay? So let's call it Alice, and Bob is someone sitting in here in a seat. Now, when the orchestra plays, everybody hears the same music, right? So this is almost like your information is going everywhere. But is there a way we can encrypt the information in the waves that the Alice, everyone is going to change the way they play, okay? Such that only this person, Bob, sitting in this particular seat, will get the exact music, original music. Everyone here else will hear noise. Just think about it. I will change the nature of the transmitter in a way that only the intended receiver will hear the right information. If I move away from the receiver, I will just hear noise. Okay? And that's what we call physical layer security. So if I just wanted to put this in a wireless communication setup, Alice is sending the information in a phased array. What happens is Alice sends the information to Bob, says a QPSK. But Eve, if the Eve is sitting on the side loop, it gets the exact same information. So Eve or eavesdropper can break into the channel, okay? But what we are trying to do is the following, which is Alice is going to Bob, which is a QPSK signal, which is very high SNR signal. But if I'm Eve somewhere sitting here, I get just noise. I just get garbled constellation. Okay, so that's what we mean by physical layer security. And we do that with, again, transmitter array by changing the nature of these. And so we build these chips operating at W band in the 71 to 76 gigahertz. And so you can see these chips here. You can see they're connected to patch antenna arrays. So these chips are all silicon CMOS foundry, in TSMC in Taiwan. The chips come back, we package them, and we measure this. And this is what we measure, okay? So on the left-hand side is a classical phased array. On the right-hand side is our proposed secure system. So how does it work? How do I think about this plot? Look at the plot on this side, where the mouse is. What we are plotting is constellation against space, okay? So Bob is at 0 degree, okay? So Bob is at 0 degree, okay? And Eve is somewhere away from 0 degree. So at 0 degree, you see if you take the projection of the constellation for a phased array, it's always a QPSK at all angles, which is what we expected, right? So if you think about a phased array, everywhere I will just get a QPSK signal. So you can see these pipes of constellation are well preserved with angle. But in a secure system, you can see the only cross section that where information is at Bob. You can see the constellation is QPSK. So Bob receives the QPSK. If you go away towards Eve, this is what constellation you get. You get complete garbage, noise-like space. You basically spread your spectrum almost like noise. Okay, so it's just a physical security. There's no encryption. There's nothing, right? It's basically a transmitter, receiver, but only the internal receiver will see the right noise. Everyone here will receive garbage signals. Okay, so you can think about the applications we showed applications in transmitter, in sensors, in physically secure communication, as well as for metasurfaces. But you can think about these applications for imaging as well. So this is a recent paper that came out. Second, where we created again on the cover of Advanced Sciences, where we basically created something like a similar kind of a sensor, almost like an insect sensor, right? Insect eyes are hemispheric, right? They're not flat. So we basically thought, why do radars have to be flat? Can they be hemisphere? And so we use origami principle, right? You've seen origami, like the Japanese art of folding paper to make different kinds of shapes. And so we use the same origami principle to create these sort of microwave imaging arrays that are reconfigurable. Just to give a sense of where origami is used in space, many cases when you have these large solar panels or large antennas that have to go out in space for deep space communication, you cannot launch a large antenna. So what they do and NASA does it pretty often, is that they collapse this antenna into a small structure, and you can see on the top, once it launches into space, it becomes large, okay? And the principle of going from the small folded surface to a large surface is through origami. They use origami, means exactly the same mathematics as sort of art of Japanese paper folding, and when they go up in space. And we basically use the same principle here, where the same surface can assume different kinds of surfaces to create very, very complex imaging systems at microwave frequencies. So you can see that the application of these frequencies is very diverse. It can be imaging, it can be sensing, it can be wireless communications, physical security, and so on and so forth. And these are very complex systems. So I'll just end by giving us some examples of a recent work where we're thinking about AI as a method of helping us in designing these complex systems. Just think about how we design the system. So right now we're building these large-scale arrays, but if you think about how people design, it's very manual. Okay, so what happens is in this high frequency, you try with a transistor, you design your circuits. Okay, and then circuits have to be designed with your electromagnetics, your transmission lines, antennas. So you design your antennas, then you simulate them together, and then you put your antennas together, and then you have to retune this, and you have to work with packaging, and the whole optimization process goes on and on and on and on, right? Very manual, very labor intensive, takes a long time. Okay, and even then it might not work. And so we started thinking about new ways of thinking about electromagnetics from first principles. Okay, so the idea is the following. Okay, so if I imagine you're designing a power amplifier, right? You have matching networks in the input, matching networks in the output. You can use transformers, or you can do electromagnetic passives. This is a quadrature hybrid, classical quadrature hybrid. And what you do is you change the length, the width, and stuff like that. You play with the Z0. For a rat race coupler, you do the same thing. You play with the circle and then the widths of the lengths of the transmission lines. For an antenna, you can play with by cutting some edges, you can make it a circularly polarized. By making a slot, you make a patch antennas. Very textbook. Okay, so we've been doing this for decades. And the whole idea is that, well, you start with a structure, and then you play with it to get the scattering parameters that you care about, right? To get the performance you need. What if we do the opposite? What if we say, well, this is the S parameter I need, and the S parameter could be a quadrature hybrid S parameter or a rat race balanced S parameter, could be anything. And let algorithms figure out the structure. Okay? Let me ask you one question. The reason we do these structures is because we understand a transmission line. Because we understand a transmission line, we understand one transmission line, then we can understand 4 transmission lines. So it's very bottom-up approach. I know the unit element, and so I can build large systems. What if we take the opposite approach? We said, I don't care about the structure. I just care about a structure that gives you the S parameters. And maybe the structure doesn't look like this. Who told me that if I wanted to create a quadrature hybrid, this is the only solution? Maybe it looks very weird. And so the whole idea of this, what we call inverse design, you start from these parameters, let algorithms figure this out, and maybe the structure looks like this on the right-hand side. Now, of course, no designer can come up with this structure, right? It looks weird, but perhaps it is better than some of these classical designs. Perhaps we can do it faster, maybe it's more efficient, maybe it's more compact, maybe you can design different kinds of structures with this, right? Maybe it's more broadband. And so we've been looking at this idea about inverse design, where we go from very top-down approach, where you go from S parameters to these structures. And so if you want to think about a PA, then you can think about power amplifiers or PAE, PSAT, S21, S12s, and maybe the whole thing looks like on the right-hand side. It doesn't look like something that we understand. But why do we have to understand it? It looks like an electromagnetic structure, okay, all kinds of weird electromagnetic structure, but all of this comes out algorithmically, which means it avoids this manual, labor-intensive effort of designing these things, okay? It's a completely non-intuitive design space. We don't know. Nobody has told us that this structure is any worse or not better than the known structures, right? Who knows? We don't know, right? Nobody knows. And maybe it is, right? So now at least it gives you a tool to explore a non-intuitive design space. We typically are comfortable in intuition, right? We understand a transmission line, we understand the inductor and capacitor, and then we can connect the inductor and capacitor. But maybe the electromagnetic structure is much more complex than that. So we've been looking into this whole hybrid human AI design, that where we can just code, right? Write Python codes for RF, and these kind of complex structures will emerge. Okay, so how does deep learning come into this picture here? So what we did was, if I tried to build this thing with generating algorithms, right? Every time you have to iterate a structure, you have to basically run the HFSS or whatever electromagnetic simulations. We basically said, let's get rid of electromagnetic simulations. Let's build a deep learning, deep neural networks, where if I give you the structure, it bypasses an electromagnetic simulation. It doesn't need an electromagnetic simulation. It goes through the neural networks, and it can give you the predicted performance. And then you can put any kind of optimization algorithm on top of it. So it's very, very fast, very, very instantaneous. Just give you some examples. So we were trying to create these power amplifiers. So, if I had a 8 micron device, this is a silicon germanium process operating at, say, 30 to 100 gigahertz. These kind of matching networks are being generated on the fly. So I'm changing from, say, the power amplifier size here, right? So 3 different power amplifiers with 3 different sizes. So 8 micron, 4 times larger power amplifier, 6 times larger power amplifier. If a human were to design, they have to start from the scratch from all of these power amplifiers being designed separately. But now we let algorithms figure out what the matching network looks like here. And you can see that it's very difficult to understand what this matching network looks like. It's not a bent transmission line. It just comes out algorithmic, almost like a QR code for your, Paytm, right? But these are actually matching networks, okay? And they work very well, actually. So this, you can see that the algorithm is emerging through this matching networks, and you can see that, at the end of the day, it creates a broadband 30 to 100 hertz matching network. And the point is that if once you train it, you can design anything. So you can design different kinds of output power. You can create different kinds of dual band systems. So this matching network does a dual band. You can create harmonic engineering. So it is a matching network at one frequency and a short at the other frequencies. You can create different kinds of filters. So these are, you can see here, this is a 70 gigahertz bandstop filter. Look at that. I mean, it's very difficult to understand why it's a bandstop, but it's a bandstop. It's a 60 gigahertz bandstop filter. It's a measured results of an 80 gigahertz bandpass filter. Again, measured results of 50 to 70 gigahertz bandpass filters. No longer sort of customized design of inductors and capacitors. It's just algorithm let it figure out. And all of these structures, you can see these are measured results, right? So there is proof in the pudding. Now you can think about as not just 2-port system, but a 3-port system. So you can think about power splitters, combiners, all diplexers. Again, these are all kinds of complex systems that's just coming from the algorithm itself, right? So it opens up a new space of AI helping us in this process and overcoming the manual, labor-intensive effort, but also allowing us to design systems that we could not design before. This is a very, very compact filter. Look at this. This is lambda by 12 on each side. It's really tiny. Okay. We have done this for antennas as well. Feel free to look at the papers here. This is a collaboration with IIT Madras on neural network based on multiband antenna design. Again, the antennas look so weird, but they are multiband and can have good radiation patterns, and all designed by algorithms. We have designed whole silicon chips with this thing. So this is a silicon chip power amplifier. You can see the matching network, the transistors, silicon germanium transistors here. The first 3200 gigahertz broadband PA. But the matching network looks weird, right? We don't know what it does, but it does very well. I mean, it beats all previous performances. This was the best paper award in IMS last year, and it works from 3200 gigahertz. It can process multi-band systems at the same time and all kinds of interesting things, right? And now people are going crazy about this. They're trying to launch programs. But when the first time we present this paper, people are like, what's going on here, right? Because nobody have thought about this. Like, why haven't we thought about this? Like, you can see that in a single chip, you have a manual design, right? These are transmission lines that are classically human design, but the output network is not human design, okay? And they all look very different, right? And then the people were blown away by the innovation, and now they're figuring out, okay, so why do we need such long design time so we can code these things? But I think that opens up a new direction. And so that's really exciting. So just give you a sense of what the future looks like, right? You're looking at the egg and trying to figure out, which bird is going to come out from. But we have giants in the field, particularly from India in the millimeter wave space. I mean, the first millimeter wave system, if you don't know it, was done in Calcutta in 1895. And this is the pioneer, J.C. Bose, known for his pioneering inventions in the radio engineering. But what's incredibly interesting is the kind of components that you had to design from scratch. Right? You couldn't go to a key site to say, well, give me a signal generator or something like that, right? So he used jute as polarizers. So you basically have jute strings that you wrap around the cylinder to create polarizers. This is a a railway book that you cut slides on them to make, again, polarizers and stuff like that. So there's innovations is been there in India for a long time in this particular space, and I think we need to grab it again, right? But honestly, to be able to do that, you really need to make from fully functional high-frequency systems where chips need to be done. There's a lot of work that's happening in the semiconductor space in India. I am bullish about it. I think new great things are going to come out from there if the training is right. So, and the training we really need to think about, broaden the perspective. Let's not get stuck into individual domains. Let's try to understand the system's behavior, from the antenna to the RFIC, to the LNAs, the mixers, the baseband, the signal processing, all aspects of it. The innovations are more and more happening at the systems level, not at the lowest functional level. So I think that we need to really think about that. But if you do, I think there's a lot of stuff that can happen across the world in the millimeter wave terahertz space, but also in India, given the latest push for hardware design, which is very, very, very important. With that, I will acknowledge my sponsors, but I'm happy to take any questions you might have. Thank you.
Thank you so much, sir. Now I request...
Paula, we use a lot of cheap, less expensive, less time-consuming, approximate simulations to build the base of the neural network. So we use some MATLAB-based electromagnetic simulators that doesn't even have dielectrics, just pure air simulations that much faster. And then we sort of transfer learn with more accurate dielectric-based simulations. And then we also transfer learn across dielectric stacks, across frequencies. So that makes it more portable in terms of you design for something, but it's not the only thing you can design for, right? So if you want to train it for a PA, you should be able to use it for LNA or a mixer or whatever, or an antenna. And so we are trying to build up a more generalized model, but I think there are sort of smarter ways of doing it rather than just learning full brute force dielectric simulation.
Okay. Got it, sir. So, one more question here. So, now, with this new technology and new things, we are able to get more gains, right? And more, a kind of milliamps and current we are going to generate it. So, with this, any heating and radiation problems are we not getting, because we are packing all the small antennas in a small single chip. So, will
Yeah.
not leads to a thermal problems.
Yeah,
How to
it
mitigate
does,
such
right?
problems?
At some point of time, it does lead to a thermal problem, especially at higher frequencies because your spacings become smaller and then your power density goes up. But it's still farther away from power densities in your sort of computer processors. We are still a factor of 10 away from it. So, but actually, it's a very important point. But especially if you use gallium nitride or some high power systems, thermal dissipation is often the bottleneck. And so when you think about packaging, you have to think about the whole process about it.
Okay, thank you. And can we use, AMC method, AMC array to boost the gains along with these techniques? Is that helpful for, in this case, chip-based antennas?
I mean, it can be. It depends on the application. In some of the cases, AMCs are very narrowband, and so that becomes not applicable for many different things. But for certain applications, for certainly.
Okay, got it. Thank you, sir.
Sure.
Others you can interact with, sir.
Don't be shy. Feel free to ask questions. That's the only way we interact, right?
Yeah, thank you very much for such an interesting talk. I have a couple of questions actually. First on the inverse design, I think it's very interesting because so far we were knowing a known pattern of fractals and other design which are following a known pattern actually. Okay, in miniaturize. And now we are talking about applying deep learning and machine learning to come up with a very undefined kind of a structure where we are able to achieve miniaturization. So as you have already told that they are not following EM simulation principle. So whether we have any standard tool available in the market or still we have to wait for that kind of tools to be available?
Not yet, but it's going to happen. I mean, it's happening in the photonics space. I think ANSYS is trying to put something together for this one. We were the first group to do inverse design on a chip, and one of the earlier group to do the antennas as well. But it's still early stages. But I think it's hopefully it's going to happen at some point. But right now, if you want to do this, you probably have to build your own models.
Okay. And another question regarding the physical layer security, very interesting thing which you have presented. Can you just elaborate more on that aspect? How we are changing the QPSK in other directions in the space?
Yeah. Sure. I mean, so the whole idea is that in a typical phased array, you're sending all the symbols to all the antennas, right? With certain phase delay, and so they go to the angle that you want them to direct at. Here, what we call, and the details are in two papers. One in an ISCC paper. If you send me an email, I'm happy to send you. But if you say, there was a paper in Nature Electronics 2021. Search my name, search security, you should be able to get it. And so the whole idea is the following, which is, instead of sending all the symbols to all the antennas, you can chop off symbols, okay? So if you have a symbol train S1, S2, ST, SN for QPSK, we chop the symbols randomly and then we send them to different antennas, okay? And so every antenna is not sending the whole train of symbols. Every antenna is sending parts of a symbol and then nothing, and then some parts of other symbols and nothing, and so on and so forth. So you can now imagine our antenna array where every antenna is sending these random chopping blocks, and only in the direction with those random chopping blocks again merge together to form the original signal. And everywhere else, because of the time delay, they will not merge and overlap with each other and then create that sort of noise-like spectrum on the other ones. And so that's the basic principle. Your space is almost like a filter, like a spatial filter. That's how I use it.
Very interesting. Thank you very much. One more question actually, because I come from the defense space. So I just wanted to know what is the roadmap for the defense, especially for the large range kind of sensors and communication. Because as you know, as compared to a commercial world, in the defense, mostly the range coverage requirements are very high in terms of kilometers or at least few hundreds
Yeah.
of meters. So how do you see the roadmap of especially the millimeter wave and terahertz scattering for the defense requirement? And as it was pointed out, the thermal problems and other reliability issues coming for high frequency. So how do you see the roadmap for the defense sector for these technologies?
Yeah, so the above 100 gigahertz is a little unclear, but there's a lot of interesting applications in broadband, right? From 18 to 50 and sort of 50 to 100, and so there are W band imaging systems and so on and so forth. And the whole idea about this is silicon may not be the solution per se for the end-to-end systems, but what we are pursuing here is we work with DARPA and many of the defense contractors like Northrop, Lockheed, Boeing, and so on and so forth. And the route is that you might need a gallium nitride front end for a PA. You also may need a gallium arsenide or an indium phosphide LNA for a noise figure, okay? So you can think about a 3D heterogeneous integration technology where you may need a front end LNA from a different chip. You may need a gallium nitride power amplifier or an indium phosphide power amplifier, but then everything else becomes silicon.